In this video, we are going to talk about electrophilic addition reactions to conjugated dienes. Okay, electrophilic addition reactions to conjugated dienes. So now in the previous semester in Chem 235, you have learned the addition of HX across an alkene. Okay, so let me write down a reaction that shows that. So for example, if you have an unsymmetrical alkene like this, if you treat it with HBr, it follows the Markovnikov addition rule, where you have the bromine or the Br go and attach to the more substituted carbon atom, and the hydrogen attaches to the less substituted carbon. Right now, the mechanism, if you recall, is where the first step is the addition, electrophilic addition of a hydrogen atom, formation of a carbocation. Carbocation forms at the more substituted carbon, and in the next step, so this is your first step, and in the next step, the Br minus attaches itself to the more substituted carbon to give your final product. Okay, so this is how the mechanism is explained. Formation of carbocation at the more substituted carbon atom. Now in case of a molecule like butadiene, which is a conjugated diene, we can do the same reaction where we treat a butadiene with HBr. However, in this case, instead of one product like in the previous case, we actually get two products. So the two products that are seen are with a Br attached here and a Br attached at this carbon atom. Okay, we call this as the 1,2 product, and this one as 1,4 product. Okay, and the 1 and the 4 are in terms of where the hydrogen attaches and the Br attaches. So for example, in this case, if you look where the hydrogen has attached, the hydrogen is over here, right? And then the Br is over here, so that is 1 and 2 position. And then in this case, the hydrogen is still here and the Br is over here, so that is your 1 and 4 product. Okay, so the formation of the two products can be explained with again a mechanism that is similar to the one that's shown here, where the first step is the formation of a carbocation followed by the nucleophilic attack of the Br minus. All right, so let's write down the mechanism on this side. Let me use the black pen. Okay, so the mechanism of the formation of these two products can be shown with the first step. So this is a symmetrical alkene, right? So we can use any of these double bonds. Say for example, the double bond here is the one that attacks the hydrogen, resulting in the formation of a carbocation here. We know that the carbocation will not be formed at this end because that's a less stable carbocation. This is the where the carbocation is formed, and then the hydrogen attaches itself here, right? So if you put the hydrogen in red color, you can locate the hydrogen here. In the next step, Br will attach on this carbon atom which bears the positive charge, right? The nucleophilic attack happens here. But remember that when you have a pi bond close to a positive charge here, this species can actually exist in a resonance form. Okay, so the resonance form of this allylic carbocation, this is an allylic carbocation, a carbocation formed right next to a carbon atom bearing a double bond is an allylic carbocation. It can exist in resonance in this manner, where the double bond moves over here and we have the positive charge over here. Okay, so let's keep the hydrogen drawn just to make the picture clear. However, you do not have to draw the hydrogen every time. Okay, now we have two resonance structures of the allylic carbocation, right? So now the next step is where the Br attaches itself to the carbon atom bearing the negative charge, the positive charge. So we have Br attacking here, or the Br minus can also attack at this carbon atom, right? So if the Br minus attaches itself to this carbon atom, that's when you get the 1,2 product, right? So I'll keep on drawing the hydrogens just to make the picture clear. And then if the Br attaches to the other carbon atom, this one here, Br minus attaches over there, then you get the 1,4 product. Okay, so here we have the 1, 2, 3, 4. This is the 1,4 product, and this is my 1,2 product. They are called as the 1,2 addition and the 1,4 addition products. Okay, so this terminology again derives from the fact that the starting diene contains a pi system where if we number it, it can be called as a 1, 2, 3, 4, right? So here we have the 1 and the 2 position. Okay, this is my 1 and the 2 position. Sorry, let's erase this and then maybe use a black color. So this is the 1, 2, 3 and 4, and same thing here, we have 1, 2, 3 and 4, right? So that results in the formation of the 1,2 and the 1,4 addition product. Now let's do a practice, right? So here I have a different molecule, but it is also a conjugated diene. Remember, a conjugated diene is where you have this alternating double and single bonds. Okay, and I am going to make this with a methyl group attached here. Okay, now if this is treated with HBr again, can you predict what are the products that will be formed? Okay, so pause the video here and then try to write down the products, and after you have completed the products, make sure that you check your answers. Okay, all right, so I'm going to go ahead and work this out. So the first step is where, say for example, I have the HBr with the hydrogen. I'm again coloring it with red color. So first step where this attacks to this hydrogen atom, resulting in the formation of a carbocation. The carbocation will be formed at the more substituted carbon atom, which is this one. Now this is the allylic carbocation. It can undergo a resonance where the positive charge can move over to this carbon atom. Methyl group is here, and we have a double bond in this case. All right, so this is a scenario where this double bond attacks or the addition happens at this double bond. Now let's complete this picture where the Br minus can attack on this positive charge, right? So Br minus attaches itself to this positive charge, and you get the product as this one here, right? Now will this be a 1,2 or a 1,4 product? This will be a 1,2 product, right? Remember our hydrogen atom, which we really do not have to show every time, but in this case, just to make again the picture clear, here is my hydrogen atom. Okay, so here is my hydrogen atom. So it's a 1,2 product here, right? Now in the other resonance structure, if the Br minus attaches itself to the carbocation bearing or the positively charged carbon atom, then you have a product which is, you have a product where the Br is at the 4th position with respect to that hydrogen. Okay, so here is my Br and here is the hydrogen. Right, so these are two of the products, but are they the only products? not in this case, because if you start with this double bond, then you will get a additional 2 more products. Okay, so let's do the scenario where the addition reaction happens at this double bond. Okay, so let's box this first, that these are 2 of my products that are formed. This is my 1, 2, and this is my 1, 4, right? Okay, now let's look at the other scenario where we have the double bond over here intact, okay, but the attack happens using this double bond. So we have the carbocation formed. So we have this intact, nothing happened to that. However, the positive charge can be drawn on this one, okay, this carbon atom. Again, a resonance structure for this one, where the double bond can be moved over here, right, and then the positive charge can be moved over here, right? It's an allylic carbocation, so you are allowed to move the double bond here with the positive charge here. Okay, now let's complete the whole reaction with the nucleophilic attack of the Br minus. So here we have the Br minus attacking at this carbocation, and in the next one we have the Br minus attacking this carbon atom. So this will result in the formation of a product where the bromine atom attaches here, and then this one will result in a product where you have the Br here, and then the hydrogen we can still show. This was the hydrogen, so here is my hydrogen, again here is my hydrogen, and Br is over here. Okay, so this tells me which one will be my 1, 2 and which is my 1, 4 product. So this one is my 1, 2, and this one is my 1, 4 product, right? Let me box this too, this one and this one. So in this particular reaction with this unsymmetrical alkene, you get 4 different products. Alright, so in summary, we can say that for a conjugated diene, you can get a 1, 2 or a 1, 4 product. Okay, now which product is the major product will depend upon the temperature. Okay, so the exact ratio of the products is highly dependent upon the temperature at which this reaction is performed. It is seen that if you perform this reaction at 0 degrees Celsius, the 1, 2 product is your major product. Okay, it's about 71%, and this one is only 29%. However, if you run this reaction at a slightly higher temperature, like 40 degrees Celsius, the 1, 2 product becomes your minor product. It's about only 15%, and your major product is the 1, 4 product. Okay, now to understand that, let's look at this energy diagram. Okay, say for example there is a hypothetical reaction where the 2 products can be formed, B and C. All right, so we have showing here A is the reactant and B and C are the product. Now B is your B is the product which is called as the kinetic product. Okay, and B is the kinetic product. That means it is a product that is formed faster, right? And then C is your thermodynamic product, because that is the more stable. Okay, so if you look at the energy diagram here, you can see that B is formed faster because of the smaller energy barrier here, and C is the more stable product, which is at a lower energy, right? Now at a lower temperature, right, what can happen is the energy of activation is the more important factor. So at low temperature, since most molecules do not have enough energy to overcome the higher energy barrier, therefore at lower temperature they react by the faster pathway, forming the kinetic product, right? However, at higher temperature, most molecules can have enough energy, enough kinetic energy to overcome the either of the transition states, and the two products are in equilibrium with each other, and the more stable product will be formed, which is the one that is of lower energy. Okay, and that stands true for our products that are formed for our with our conjugated dienes, electrophilic addition of conjugated dienes. If you recall the mechanism of the formation of this product, the carbocation was formed here, right? So this product is more stable kinetically because of the more stable carbocation, and that is the one that is formed faster. Okay, here it would be a primary carbocation, right? So a primary carbocation is less stable than a secondary, therefore this one would be formed slower. So the reaction which will be faster would be the one that has a more stable intermediate, which is your secondary carbocation. But with as the temperature is increased, more and more molecules can cross over that energy barrier, as a result of which the thermodynamically more stable product is now formed, which is your 1,4 product. Okay, and why is this the thermodynamically more stable? Again, recall from Chem 235 that the more substituted alkene is the more stable one, right? So this is the less substituted alkene, and this is the more substituted alkene. Okay, so we can write it here that our 1,2 product is the kinetic product in this case, okay, and our 1,4 product is the thermodynamic product. Right? This is my thermodynamic product, which is the more stable. So at higher temperature, the thermodynamic product predominates, and at lower temperature, the kinetic product predominates. Again, remember that kinetic product is related to the more stable, we can write it here, more stable carbocation, and thermodynamic product is related to the more stable or related to the more stable alkene, or the more substituted alkene. More substituted alkene. Okay, so I hope you have understood the reasoning of why how the temperature controls the major product of this reaction. Lower temperature results in the formation of a product which involves a more stable carbocation, and at higher temperature results in the formation of a product which has a more substituted alkene, which is considered to be more stable. All right, we can finish this up with a final example. Say, for example, if I have an alkene like this, again it's an unsymmetrical alkene, and again you should pause the video here and try out the products and the mechanism for this reaction by yourself before you continue to watch the final solution of this. Okay, all right, so how many products do you think will be formed here? Okay, again remember that there are two different alkenes, so you can either show the attack from this first or from the electrophilic addition over here. So let's start with this one here. So my first intermediate would be where I have we can keep this double bond intact, and I can have the positive charge here, the carbocation. This will be in equilibrium, in resonance. You can form the resonance structure of this, where the positive charge now moves over to this carbon atom. Right, so let's keep on drawing the hydrogen so that so this is my hydrogen, the hydrogen is still here, right? And this is the resonance structure of that. The formation of the product would be, oops, I can still continue using a black pen here, and we have the Br over here, right? and the hydrogen is still at this position. The next product would be here. We have the double bond here, Br over here, and then the hydrogen at the first position. Okay, let's box these two products. So we have one and this one. Okay, now let's do the reaction where this double bond attacks. So that will result in the formation of the carbocation that will be formed. So we have the hydrogen on this end here, and then the carbocation formed over here, right? Resonance structure for this one is here, right? And then the positive charge moves over here. My hydrogen is still at this position, and it results in the formation of two products again, which are Br at this end. Hydrogen is still over here. This results in the formation of a Br at this end, and then we have the hydrogen over here. Okay, so we have four products with this unsymmetrical alkene again. Now can you tell me which one would be the kinetic and which one would be the or which products will dominate at low temperature and which ones will dominate at the high temperature? Remember, at low temperature we have the kinetic product, okay, which is resulting from more stable carbocation, and at high temperature we have the thermodynamically stable product, okay, the thermo product. Now if you look at, we have 1, 2 and 3 alkenes or double bonds which are di-substituted, right? This is a mono-substituted alkene. So this is a mono-substituted alkene. This is a di-substituted alkene. This is a di-substituted alkene, and this one is also di-substituted alkene, right? So at high temperature we can have these three products as the major products. Okay, so let's call them as let me call them as A, B, C and D. So at high temperature the major products you will see are A, B and D. Now at low temperature, which is my kinetic product, will be the one which is related to the more stable carbocation. In this case, this is the secondary carbocation. We have a secondary carbocation, we have another secondary carbocation, and this is a primary, right? So the major products in the at low temperature would be A, B and C, right? So that's how you will decide what will be your major and minor product based upon what kind of different substitutions you have for the double bond, or what kind of stable carbocations are formed during the reaction. Okay, so this concludes my discussion about the electrophilic addition reactions on conjugated dienes. Make sure you practice a few more examples from the textbook before you move on to the next section, which is our Diels-Alder reaction.